Now do you hear me, Tamir?
Yeah,
very good. Okay. Okay, let's start with, let me remind you, we will talk about Dwyer-Kan localization. It's like a natural generalization of the homotopy category for some model category, or even it doesn't have to be a model category, it has to be something with weak equivalences. Okay, let's start with, remind you, when we have a category C with W, a subcategory of weak equivalences, like I have this property of 2 of 3. Okay, when we have this pair, we can build it from there the homotopy category, because actually what Igor did, he did this for model category, but actually he did this just using the weak equivalences, right? It depends only, we know that by the only on the weak equivalences. Let me remind you what is the construction to build this. Okay, of course, like there is other way to do this, but in order the construction, the real construction of this, it's like this. Like we take a map here will be in here, a map will be something like this. Like I have zigzag to y. When this actually is something in W, like this is the inverse of something from W, this one, okay? This also can be in W, this can be, okay? So it's something like this, like we invert things in W, okay? Like we can, of course, like we can put something like this, two maps, it's in C, two maps, and then map like this from W, but we can compose this to get just one map. So we can think about this as zigzag like this. When we added this, like this is the maps from W. So formally it's like this, and the composition, like we just put chain after chain. This is the composition. And when we have, of course, identity is identity. When we have to like this, we can compose from C, the composition from C. Okay. So this is a building of, this is actually something general for localization. Localization over this, we make it invertible. And we have this property, this category. We have the category C. Then we have this functor to this category, the obvious functor, because every map in C appear here, right? Like just one. Yeah. We have this, and if we have a functor, this is the property, the universal property. Every functor that send every W here, everything in W, every morphism in W to something invertible here, well, we can replace this by one functor from the homotopy category to D, okay? This is the homotopy category, but actually the homotopy category doesn't really capture the homotopy information we have in W. Actually, people know this from too long time ago that, okay, moving to the homotopy category will lose money, higher order homotopy information, okay? Let me show you one example. In top, given the following square in top, we are in giving the following square. This is the circle, this is the disk, and here is the sphere. Okay, this, and the other one is this. Or we can put here all points. Okay. Now this square, commutative square, if we down to the homotopy as a square in the homotopy, will be the same. Will be the same square. Actually, like everything here is fibrant and cofibrant in the topology space. So actually, if something is the relation in the homotopy, we can do this by the homotopy relation, and we know that this is contractible because the target it's contractible. So this is non-homotopic. Sorry, the map non-homotopic, and so this homotopic to the constant. Okay, so this will be the same in the homotopy category. So this square will be the same by projection this, okay, but okay, or by going to the here. This is also commutative square. Like I choose a point here, unique point, like this is pointed maybe topological space. We can think we have a point here, fixed point. But actually, this is not the same in the real world. Like if we think about the world of squares, in the square, this is not equivalent. Like we don't have a zigzag of weak equivalence between this two square. We don't have this. Well, one can't show this because here actually we have some invariant that decides the homotopy type of this square. It's not just the maps. The maps, all the maps here and here is the same, but actually the hidden things is we have a map from the homotopy co-limit of this, the homotopy push out of this to here. Okay, we have such a map. So from this square, actually, it's already cofibrant square. So this map will be actually the S2. So this map will be the identity. For this one, of course, we have to do here. I want the homotopy cofibrant, so I have to replace this by. I have to first of all to replace this. Okay. Cofibrant replacement to do to this, and then this is okay. And then to do the homotopy push out to this. So we get this square. We get this square. So then from the push out of this, which is the same homotopy push out of this, which will be again S2, and the induced map here will be constant. So this actually not the same homotopy type, right? These two maps. So this show because this is actually invariant. What we did now, it's invariant. Like if we have two square and there is a zigzag of weak equivalences between them, then this will be when this induce weak equivalences between this, but we don't have between this. Okay, between these two maps. So what?
In the zigzag, are you taking everything to be a weak equivalence, or just the ones that are pointing to the left?
No. All yeah, zigzag of weak equivalences. This is actually the like we in the top as object we say that two objects in the same type if we have equivalence between them. Yeah. So this actually in the world of squares. There is also this is also a like a diagram of this shape. There is model categories that induce from the model category we have in the original category. Okay, so we see like all we can think. Forget about maybe someone say okay this is in square world, but this actually there is a homotopy invariant here that it's we can't see how we can do this homotopy. We can't build this in the in here in this category because in this category this two square will be the same. We can build this map because we see that here is different. This map will be different. This is actually homotopy invariant. So it's higher order homotopy invariant that we can see here in the. So there is more also much higher than this that we can see. So actually it's obvious that this is actually just the zero floor of the homotopy information. And when we down to this is not good shadow. Okay. This forget many things, many important higher order things. So actually the idea of Dwyer-Kan that we have category that we try to put in this category the homotopy information, but category it's not good to put the homotopy. We need infinity category, infinity one category in order to put this. So instead to do this like the homotopy, to go to the homotopy category, they built what called Simplicial. They called it, even in their third papers, they called it Simplicial homotopy category, the Simplicial homotopy category of the category. Okay, and then this will be the zero floor of this. Like this will be the homotopy for this. Oh, we will see. Okay, so let's see the Dwyer. Okay, I can continue there. The hammock. The hammock construction. Okay, so instead of this, what Dwyer-Kan suggest, they said, that's why I wanted to here to remind you how we build the localization, because it's something from the same spirit, like something from, but generalization of this. Actually here, okay, here we did in the zero level. This is the zero level, like, but actually we allow the rule that here there is the rule also that if I have like this, and then I have this, that like this, for example, this is f and this is f minus 1, then this is the same as the identity here. Okay, in here rules, I forgot also to tell this rule, but there is a relation. It's not just okay this, but there is some sequence like this will be equivalent to other sequence the same. Like we divide by this relation. Like for example, this we forgot about this. I have, for example, 2 square like this, then I forgot and I put fg. Okay, but actually in the zero level of the construction, we forgot about this. Like we can put like this, and this is not equivalent. This is not the same as this in the zero level. So we will see. So in the n, let me show you the n level in general. So given CW, again, what I mean by CW, a category and some subcategory that have this property of 2 of 3. Okay, is this called the category with weak equivalences? No, the object can be not the same, not every, between every, okay, the same, sorry, because the identity have to be this here. Yeah, the object is the same, sorry. But the morphism, yeah, not the same. Okay, so we have this, and then what we build now, we build for x, y, and z, we build these things. xy to be the following simplicial set. This will be simplicial sets, not just the set. Okay, it's okay. The following simplicial sets, sets that I will how in simplex it's look like here. So in simplex will look like I have this x. Okay, sorry, someone like this, someone like this, and continue until we go to y, and here, and we have another floor. Okay. But we see in the same direction, like in every level, the same directions. Like if here the direction it's like this, the direction will be like this everywhere. Okay, because it can't start it with this direction before, but zigzag like this until we go here. Now the level will be n, like n floor we have, or n plus 1. Just a minute. No, n plus 1, because actually the 0 will be this. So n plus 1. N plus 1 arrow. And all this will be weak equivalences.
N plus 1 which way? Vertical, horizontal? This way, right?
Yeah, arrows, n plus 1 arrows. So n plus 1 arrows. Like, yeah, in In this, in this, like like this, what is decide. This can be any length, can be any length. This can be any length. But this is then this what decide. So this all equivalence, and all this will be also equivalence. The inverse of equivalences. All this can be equivalence, can be not. But these ones, it's all of them equivalences. Is like the inverse, like this shows some inverse of equivalences. Okay, this also like the other the opposite direction of some f in W. Okay, this also all this direction.
The opposite, it feels like it's going from left to right.
No, I mean like this. Yeah. Okay, the direction. Yeah.
I would think that it's going from left to right.
Like I mean, like we have some f. This will be something like f minus 1 when we have some f in W. Okay, for this f minus 1 for some.
But then it's actually going from left to right. That's what you mean.
No. It's going like this. It's going like this.
There's an f that goes from left to right.
Yeah, there is an f, but I wanted here the f minus 1, not the f. Maybe I can put the f here.
Yes.
Maybe here f another f, but this means f minus 1, not the f. Yeah, okay. Like in the localization, what we're doing there, the same construction, but here this is, we don't have this relation like if we have f and after that f, I will compose with them. No, I don't have this relation. This actually will come from the first level, from the other levels. This will come. Okay, we will show this. So this actually is the ensemblex. So what is the degeneracy map? What is the faces map? It's obvious. Like the faces map, we forget. Like for example, D0, I forget about this, the first one, right? Like by imitate one of the, by composing also. Like if I is D1, so I compose this both. Okay, so I will be less level. Exactly, like the same rule. If what is the degeneracy? By adding the identity. Like I can add here all the identity, right? And added this the same floor, or here the same floor by adding the address everywhere. So this is the degeneracy. It's obvious, and we need to show that this is a simplicial category. It will be like this is enrichment. Like we have here composition. So how the composition look like? It's also obvious. Like if I have this here, product from this to this. Okay, product will be the same product in the n place. And then we get something here, such that this will be simplicial. This like in the n place, but this actually, if we continue, this will be simplicial map. Right? It's obvious. It's obvious what is y. Like I have something from y, z here. Another one, continue. So what we're doing, actually, we compose like by what is called contractive, like by put this and then put this after. Concatenation, concatenation. Okay, so the composition by concatenation, it's obvious. So we get actually a enrichment by simplicial set. So we get simplicial category, like from C, this will be simplicial category. So for C, W, we get L, C, W, a simplicial category. Category enriched by simplicial sets. Okay, that is. But in this simplicial category, there is a better property. Actually, this includes, we will show the first thing that this includes the old construction. But there is another beautiful property that maybe the last things we can say in some cases that really it's this actually capture all the higher order information. this construction. Okay, let's see. So first the properties, move to here. Okay, I can continue there. Okay. First properties we have here. Properties. First, actually, this is functorial construction. One can see it's not hard to prove, to check that this is a like LH. Actually, it's some functor from category with weak equivalences. The word of categories with weak equivalences. To simplicial categories. Okay, this is functorial construction. The other things, the other things that actually we have a functor from, we have a functor from C to for some C, okay, for CW, I can, no, I want just C as a category, but actually functor here, I mean functor of simplicial categories, but one can say like just a simplicial, you know what it's mean, functor between simplicial categories, okay? Like Igor explained this last time. So functor between, but one can say this is just the category, but actually every category we can think about this as simplicial category, like it's enriched by sets, but these sets I can think, I can add identity, all the digits and faces map, I can add in every level the same set, okay? So every category, it's infinity category. Quasi we show this, and also here it's in the sense of simplicial categories, this is simplicial category. So we mean this. So there is a functor. What this functor doing actually for W, before we have like, we have this like from C to OC, that every W here going to invertible will be invertible here, but now no, it's not, it will be equivalence here, okay, such that every F in W sent to an equivalence. We know what is equivalence. You remember, like we have equivalence, we mean in the old sense, like what we know about topological space. Like I have here equivalence here, we mean that in the zero, this F will be in the zero level, like F from X to Y will be in the zero level of this. So there is something from in the one level, like there is H here, and there is another map here, like this is F, and there is another map here, G, such that the composition will be homotopic to the identity. Like there is someone from here such that D0H will be this. This is something here in the zero level of this, and D1H will be the identity. Okay? Let's see actually this. Let's see why this is correct. Yeah. It's not that obvious, right? Maybe it can show you why this construction, why we imitating like this. We removed this, that if I have something and the inverse after, we not compose in the zero level because we had this in the one level. Okay, I move here. Let's prove this. But so if we have given f in W, and then we move like this f, okay, from x to y, f like this. This will be, actually, we know that this will be 0 simplex in here, right? This will be in the 0 level of this one, okay? 0 simplex here, but, or here, I don't know how to, this is a 0 here or here. And we know that because this W we have here also, we have also this one. This we allow this here. Okay? We have this. And we have the composition between them, like this, and then this, right? We have the composition between them. But we have one simplex like this. We have this one simplex to put here the identity and to put here f. And then I put here, like, because I allow this allowing, because this is equivalences, equivalence, and how I can continue here by putting again x and here x. So this is a commutative. Yeah, I didn't say this is a rule actually about can we move here? Can we move? Sorry. Yeah, I forgot one of the rule. Actually, yeah, so to be honest, like this, if you going to the definition in the first paper, there is a 3 paper actually, Dwyer-Kan. There is a 3 paper in the 80. 3 papers, so 1, 2, 3. This maybe more appear in the second paper of this. So if you going there, you will find the definition will be many explains the definition, like maybe 6 axioms that explains the definition. So I didn't tell them because some of them obvious. One of them that this is all commutative. So one say, okay, but there is this direction. How you say that this commutative? What you mean by this commutative in this direction? We mean that we allow here in the, we don't allow here this, but we allow here this, that if I have f minus 1 f, then this is identity. Okay, I didn't say this, but this is the rule. This is the definition. Okay, so the definition is that I don't allow, like if I have f here, I can say that, oh, this is the identity. No. But if I have here, yeah, it's mean. Like here, all this commutative, where it's commutative in C with plus that we have this f minus 1. That we have also, like if I have f minus 1 f, this will be the identity. Okay? So all these squares here are commutative in this sense. Yeah. So let's back to this. Yeah. So this will be commutative. Actually, I have to do this even to be the same actually. Yeah. So we have this, and we have here what we put here, f minus 1. So actually, yeah, this is square actually commutative because of this rule. No problem. Yeah. So f minus, we can do this when in this squares. This is actually square in the sense of this. I can write it like this. I can write it like this. Like, I don't know if I start it like this. So I can write like this, and then I can add identity here. Yeah. X, Y, where is Y, F? Yeah. Yeah, if it's more obvious. So this actually, I can use the rule in this square. Again, this is the definition. Like the definition is something formally. So the definition, let's back to this, sorry. Yeah. Yeah.
How do you start from? Which node do you start from?
I'm here. This one in what I mean, like this is in LHCW1 XY. Now, you agree or not? Let's see. So, yeah.
And then, no, the other one.
Yeah.
Go to left.
Yeah.
No.
No, it's commutative like this one.
And then down.
Yeah. Yeah.
If you go the other way around, it's
F
F inverse.
inverse. So F inverse will be the identity. The identity.
How is that commutative? F inverse are different things.
What different things? No, f inverse, we don't have f inverse in C, right? We don't have this formal formal notation.
Means you go from identity, you go like identity F inverse. This is what commutativity means, right?
If you have f and f minus 1, it's identity. We define.
Clear,
But what?
Here, how do you compose F and F inverse?
Because we don't have this in C, right?
No, I mean the diagram is wrong. Probably there's a typo somewhere.
What's the problem? This with this, maybe here, or this with this. They're the same.
Middle diagram. What are the arrows? So which direction are you going? So the identities.
The identity here also. The identity here.
Okay, and then the top identity to the left.
Yeah.
Okay, just start from the node, right corner. And
Yeah.
start composing. You get F is equal to F inverse.
Or this. You can put this. You can put this if this you like.
Consistent with the diagram over there. You can't do one to the right, one to the left.
No. Yeah. No, we can. Actually, this is just Let me explain this. When we put this in the diagram, when we put this, we mean this map from here to here. But we put this. This is what confused you. But we put this just to remember that this is not actually a real map in C. This we put it as a notation.
Oh, okay. So
yeah.
I was asking why you went the opposite. Okay. So
Yeah. Yeah, this map actually from here to here. This map actually the f minus 1 from here to here.
From left to right.
Yeah, from left to right. But yeah, it's like an.
Make it commute. Oh, wait. But still, it's not commutative, right?
Why it's not commutative? Like
you
f.
Go F down, and then you go F again. It's
F minus 1. No, this is f minus 1. This is not f because f from x to y. This is from y to x. This is a formal. Like we don't have f minus 1 in C. Let me again explain. Let me again explain. We have maybe in general how we build this category. Like for example, how we build the category of here to define this. To define this, how we built, we added these formal things. Like I have f and I add here something that called f minus 1, right? Okay. So let's say maybe this, we can say from the beginning that every time in the zigzag, in this, like from n simplex, the definition of n simplex, that we have all in this arrow, but one of them it's something in C, maybe can be in W. The other one, it have to be this one, f minus 1 of something in W. One like this, one like this. We can define, this is the same. We can define like this. Okay? All the arrow like this.
Yeah, I'm okay with the horizontal arrows, but right, what do you mean by
yeah, so the commutativity here of these squares, here all of this have to be equivalents. Okay. So when we say that something commutative here, when we say, so we mean that it's commutative or in C, because in C, or maybe plus this relation that if I have f minus 1 and then f, this is identity, plus this relation. Because f minus 1 not in C, this is something formal that we added. So if I have, so now we put all in this direction. So this f minus 1, I put in this direction, and here f.
But isn't it supposed to then f minus 1 go from y to x?
Yeah, from y to x. So it's going from y to
so
x.
it will not do that way.
Yeah, from y to x. No. Forget about this. Maybe this direction make you confused.
No, now it's correct. So you
Yeah.
put the other direction before.
Yeah. Okay, forget like everything we put in this direction.
The other direction doesn't commute. If you change the direction of arrow in F inverse,
Yeah.
change the arrow, it doesn't commute that, right?
No, but when I put it this, like when I put this, I didn't mean that this map from here to here. No, I just wanted to remember that this map actually not a map actually in C. This is the inverse of map that we have. Okay, this is not we want just to remember that this map is not a map on C, actual map. This is just a notation of f minus 1 that it's going from here to here.
What is the correct direction then?
This is the correct direction, like f minus 1 and then you have the identity. This is the identity because we like this is.
Okay, so anyway, in a category,
Yeah.
when you compose things, you should be consistent. If you put that F, then the F inverse is supposed to be the same direction.
Yeah,
But
okay.
it is not in the same direction.
Yeah, here, yeah, it's the same direction. Let's forget about this. The definition, okay, so
It's correct, but the other one is not.
which one?
If you go to the left.
Which one? This
is
one?
correct. Yeah, the other one.
No, but what I meant by this is just to remind us that this map not in C. This is the inverse of some of the map from X to Y. Okay. This, if you look at the definition of this, they do this like this, and they say that this one we mean that.
But if you put the arrow to the right, I agree. But if you put to the left, it's
we can. It's just a notation. We can do why? It's just a notation.
No, I mean, if you okay, so there's of course the notation there.
Yeah.
If you fix your category and if you decide the directions are supposed
No,
to
no. When I want just to remember that this map, it's not a map from F. This map from here to here, but it's not just a map from F. It's the inverse of F. If you understand this like this is good. So it's the same. Yeah, it's the same. So here, what I want to convince you that actually this one.
If the arrow is like this, it's trivial. Yes, I agree.
Yeah.
If the arrow is wrong, it's wrong. That's just this simple. I mean, if there is no mistake anywhere, and if what you told me there is correct, then yes, the arrow is supposed to be that way. You can't change it.
So we have actually F and then F minus 1. We have this one.
Everything is consistent if you put it this way.
But it's okay to put in this way. What's the problem? I don't see any problem here in this. Okay, so we have this actually, these ones. This like in the 0 and this is the 0, and we have in 1 d0 of this is this, the composition, and d1 is this. This exactly says that this.
I think there's a mistake somewhere. So you want to put the F inverse to the left. If you want to put the F inverse to the left, I think you should. The diagram is supposed to change. I think there's a typo somewhere. Normally you want to put the F inverse to the left to be consistent, right?
Yeah.
Okay. I think there's a problem with the diagram somewhere.
So you want this, you can move, you want this to be really F minus 1 here.
No, I don't want anything. I just want.
And then this going like this.
No, okay, so let's fix
this and this is the same.
No, I don't want to change the rules because you haven't written down the rules. I don't know what the rules are. So if you want to write the F inverses to the left, like that one,
yeah,
and you want to write the F inverse over there to the left, I think there's a mistake in the diagram. But anyway, okay, it's not.
We can, like, this definition actually can't change. It's not like it's just about what we accept. But the idea of this, like, the idea why we get new things, actually, that we forget about this. Like in the homotopy, we have this relation. Like if I have this, so this is exactly the identity. Okay? This is the idea. So we have this identity in here. This relation, we have this relation. So this will be the same as this. We divide by this. We make them the same. But here, no, we don't make this is the same. We don't make this the same. But what we did, actually, we have this square, and this one simplex can tell us that is the same. So, yeah, this is the point. So actually, about notation, how to do this exactly, like, or to.
I'm still confused. Anyway,
yeah, okay. Let us move to. It's something technical, like, yeah, but the idea is this. Something we can agree, we cannot agree. We have to work on this more, maybe. Okay, let's move on. So actually, what we're showing here is that we have here from C to L H CW, we have this functor actually, but here if we move to this, and if we move here to how we solve this, I don't know, like the 0, pi 0 of this, we know now that everything's here going to invertible here, right? Because we show that everything here going to equivalence. So here it's going to invertible. So we have a unique map from here to here, but actually this unique map will be equivalence of categories. Okay. This is the important things. So actually what we built, actually Simplicial, this is why people told it Simplicial homotopy. Like this is the homotopy category, this is a Simplicial homotopy category for this, for CW. Why? Because actually this is generalization of this. We see that in the zero level, pi zero of this is exactly the homotopy category of C. Okay. So this is one property, the other property. Now what we have another important property when we move to model categories, because so far we did everything when we just have a subcategory of weak equivalences. What if we have, if C is a model category? Okay, if we see is a model category, one thing we have, it's that this. Now in model category, I will use this notation, okay? Because we know what is the equivalence. The equivalence of the model category, okay? I will use this notation. I will not emphasize the W because it's known what we mean by W. So if we take this subcategory of cofibrations and we go to C, this will be Dwyer-Kan equivalence between this, because this is simplicial category, this is simplicial category, this will be equivalence in the sense of Dwyer-Kan. What Igor explained to us last time. The same if we take the fibrant, this will be Dwyer-Kan equivalence. Okay. Second things, this is the important things that what we have. Yeah, Dwyer-Kan equivalence, we mean like when we have when you have two C and D. Yeah, exactly. So you have, yeah. Let me remind you, maybe someone don't remind you. If we have two, like then we have for every xy, this will be weak equivalence as a simplicial set. Also, if we're going to the pi zero of this will be all equivalence of categories, okay? Pi zero also will be equivalence of categories for every xy. This is what the Dwyer-Kan equivalence say. One can define it a little bit different, but it's the same. Okay, so we have this, and also the other things that if we have between two category, model category, Quillen equivalence, then it's give me Dwyer-Kan equivalence between these. Okay. Both of them, like both direction, we have adjection here. We don't have adjection here, but both of them are Dwyer-Kan equivalence. When I mean equivalence between two simplicial categories, we know because we already defined like a model category for this for simplicial categories. Okay, so we mean Dwyer-Kan equivalence. Okay, so this is also we have. This shows that this actually it's invariant. Okay, this is invariant for model categories. Now let's move to simplicial model categories, because there is the important result that Dwyer-Kan have in their last paper of this three. But we need to define what is simplicial model category before this, because what at the end I want to say is that if we have simplicial model category, like what it means simplicial model category, like model category plus simplicial category at the same time, but they of course have something that connects between the homotopy theories of these two and the categories as categories and as homotopy theories. So this here or here? Over there. Okay. So what this says that for every, if I have model category and they have simplicial construction, in some sense it will be this one, the hammock, this one, the Dwyer-Kan localization, something like this. We will see at the end, but first of all, because we didn't define this, what is simplicial model category, so let's define what is simplicial model category. I need this define, yeah, just, yeah. So definition, simplicial model category. It's again, it's model category and simplicial category at the same time. Okay, so we have, so at the beginning, okay, it's what is this? It's a simplicial simplicial model. Okay, it is what it is. It is a category or a model category C, a model category C. So actually, we will use this notation. Let me, because it can confuse like this. Okay, this I will use this notation for morphisms, for the set of morphisms. And we have such that enrich by simplicial set. Okay, so we will use this notation for the enrichment. What is the notation I want to use here? Home. I think the same notation that Igor used. Such that now we have some properties. The first property, of course, like we need at the zero level of the enrichment to be like the same as the object. Okay, this is the first property. The second property, it's like that for every A in C, if I have A in C, we have, there is left adjoint for this one. This functor actually will be from C, right? This functor from C, I put here C, and this gives me simplicial sets, right? This is enrichment, like from. So there is left adjoint of this. We have left adjoint. Okay, we have that left adjoint such with this property such that there is a natural isomorphism Okay, I will explain this, but later more actually. But it's mean here, you know, like simplicial. This is XY simplicial set A in C. Okay, if we do the product here and then we do this, this is not tensor product. This is a notation that Quillen used at the beginning. So this is not a tensor product or something. That's notation here. Like it can be like in simplicial sets word is just a product actually. So this is the same as this. If I product in simplicial set and then do this, this will be the same to do like it's like action of simplicial sets on A. This is what is this. So this act and then this act is the same. And we have also the third thing that we have for every A and C, we have this one, or for every B, I want to use here B because just to to remember this better, we have this from Simplicial set opposite to C, a left adjoint for which one? For this one. Now, also this one will be but contravariant functor from C opposite to Simplicial sets. Okay, plus 4 plus SM7. I will explain. This is the homotopy, the relation between the homotopy. Okay, I will explain after, but I want to explain this 1, 2, 3 before. Okay, we will write later. Because actually 1, 2, 3, nothing to do with the homotopy theories between theory between the model category and the simplicial category. What? Did you? Sorry. In simplicial, just a minute. What? Yeah. Actually, yeah. If we take the simplicial sets, actually, this will be the number 3. Will be the map. B bar. Yeah, the map actually. From like you have map B. This one. This from simplicial sets opposite to simplicial set. Yeah. It's the map actually, and this will be the product, the regular product. Yeah. Let me explain the first 3 things. Again, I want to say something that 1, 2, 3 actually give me just the connection, like the category to be simplicial category at the same time. This is what we need. But without any things about the homotopy theory between the things, because the homotopy theory in the C, in the category of cells, is because this model category is coming from the equivalence from 5 rank of 1 can, but it depends only on the equivalences, and the homotopy category in the enrich, it's coming because we have this homotopy there and higher order homotopy. We will connect this here actually. But before, let me explain what it's 1, 2, 3 give us, what it's mean. So we can replace 1, 2, 3, and I think this is the original definition from Quillen. The 1, 2, 3, 1 plus 2 plus 3 give us the following. Actually, that give us this, that we have this. Now I replace this, like for every, I fix x, okay? For every x in simplicial set, we have this from C to C, okay? Like here. If I now fix x, okay, like for every x, this gives me object here. But actually, it will be functor in this case from C to C. And we have the other functor, it's this functor. Again, I replace here from C to C also, which is adjoints. We have this pair of adjoint for every x. What is this adjoint functor? This adjoint functor that give me the higher order. This in C, on C, but this give me the enrichment. How it give me the enrichment? Such that this will be the enrichment of some AB. For some AB and C, the enrichment will be exactly, or there is a natural isomorphism to this, like C. Or because it's enough to say this, but because of the equivalence, because of the adjoint here, we can replace this by saying A, right? Yeah. Yeah, N, exactly. It's equal to this. Okay? So this is the relation. Actually, when we have simplex, we have to think about this like this. Like the N simplex, it's coming from some product there. by delta. And what we have in mapping, like how we get from simplicial set the map, the enrichment, right? It's like this. So this is what we have. Actually, we have to think about this, and this is actually the original definition of, I think, is the of Quillen. But with this, of course, with this property. So let's explain this property. Now I move to here. Yeah, I wanted the okay. Okay, the last property is M7. This is the important property that connected between the homotopy theory, like because we say, okay, model category and enriched category by simplicial, like simplicial category at the same time. So here we have homotopy theory, here we have homotopy. So this connection will be here. So what is this property? The property says that for every, use the notation here, for every, if G from A to B cofibration, I mean in cofibration, okay, and Q from X to Y fibration, then let me show something. We have actually, we can move from B X here from C, we can move from here to A X by applying G, right? Like by composing by G. So what we apply here is this one, right? So, and we can go to here. We have all the time, we have this square when we have this map. So we can go to here by applying this one. So Q, A, Y, but we can apply first of all Q and then G, right? So here we move by applying Q to B, Y, and then we apply Q. Okay. So actually we have here a map from the pullback of this. There is induced map from the pullback of this B, Y. To here, and the condition is that the induced map is fibration. If this is cofibration and this vibration, okay, the induced map is vibration. A vibration where? But it can, let me say it can vibration to just to confuse, because this is in the world of simplicial sets. Okay.
Why was that called SM7? What part? I think the part of the model is the part, right?
Yeah, it's there is CM4, like I don't know. Yeah, there is.
Is it CM or is it SM?
I don't know actually why it's SM. No, not CM. No, SM. The other CM, I remember. The other ones with the SM7. I don't know why. Yeah. Actually, this is the things, and here we, let's explain what is this give me actually. It's obvious that it's connect between the vibration in the simplicial sets and vibration cofibration. This one, sorry, I have to say something. If this is one of them, if J or Q is trivial, one of them, then the induced map will be trivial confibration. Like a plus, if also like it's a trivial, if this is trivial vibration or this is trivial cofibration, this is the induced map is also trivial. The first things actually we can see here, yeah. The first thing we can see, we actually start a little bit late, yeah. So we can see, okay, proposition. Let's say if j is 1, if j from A to B and x is vibrant, then actually the induced map by j, like we have induced map from home will be a Kan vibration, okay? Home A. Yeah. Of course, if we add here that this is trivial, then this will be trivial. If we add that this is not just vibrant, like weakly contractible vibrant, so this will be trivial. But how we can get this actually? Let me maybe do the dual of this. If we have Q, this vibration, and A is a co-vibrant, or B, I mean, yeah, no, it's not a problem. It's not a problem with this A or B. Okay, home. Then the induced map, Q, will be, again, is a Kan vibration. Actually, why is it true? Because actually one can, like, okay, let's maybe put here, which one I want to do. Where is it? So if we put here the, which one we want, like, for example, if we want this one with the, this is co-vibrant A, so we put here like from A to B. I want B actually, but it's A. Okay, no problem. Like this, if this is just like this is vibrant, the B. So this is co-vibration. So if we put here the empty, or now here's the empty, yeah, and here's the empty. Let's say B here, I use, but it's the same. Okay, B here, or which one, or the first one? I start confused. Sorry. A is a co-vibrant. What I did here, yeah. Here it's also there is a problem here. Yeah. Okay. B. Let's put B here because I use B there. Sorry. Yeah. So actually one can say, but here is the point. Like this will be a point, just a point. Actually, why this will be a point? Because actually this one is the same as C, like, or the n place of this, the n of this will be the n place of this will be C, this tensor with delta n x, right? The n place by the what we said there, and actually we know that this functor from C to C, I mean by this the initial object, okay? Someone asked me, this is the initial object, I mean. Okay, this functor, actually we know that it's have this left adjoint of the other one. Like we say that this and this is the right adjoint, that this is the left adjoint, so it's a preserve co-limit. So actually this will go to C empty x, and C empty x will be just 1 point, okay? So this will be actually 1 point, and this will be 1 point here. So actually the co-limit of this will be exactly, and the induced map actually will be just this, the induced map, okay? So this why this hold, and this is the same. But maybe this explain more than this complicated, because this gives us other things, not just this. But one of the things is this, and this actually says that this functor, like this functor, which functor? This one, from C opposite C to simplicial set. Here we have a model category, and here we have also a model category. This preserve, in some sense, the model category structure. Was sent like vibration to co-vibration in this, like in the opposite direction. So here, vibration to vibration. Yeah. So in some sense, it says that this preserves the model structure. The other property we get from this okay, let me back to this. I can explain here. So we just put here. Okay. A, it was. I back to here. Actually, the other things I want to explain that we can get from this we can get the lifting property actually from this, because actually what is the lifting property? Tell us the lifting property. I mean, if I have okay, this is A, back to A. What is the lifting property? The lifting property tell me that if I have AB and here XY and here one map here like S and here some K, okay, this is J, this is Q, such that one of these are trivial, like this or this are trivial, then we can lift, right? But actually we can get from this easily in the zero play, in the zero here, we can get this in the zero level. How we can get is that, because actually what it's telling me that this is here, this is Kan vibration, right? Trivial Kan vibration. If one of this trivial, so this will be trivial Kan vibration, right? Then, but actually trivial Kan vibration, if we have trivial Kan vibration, like for some map, like, okay, what I can use here, which CD something, and this is trivial Kan vibration. So actually it's surjective in every level, because if I have this will be, so it's surjective in every level. Trivial Kan vibration surjective in every level. So it's surjective in the zero level. And if we take the zero level and we think a little bit, if we take the zero level, it will be here, the zero here, zero here, zero here. So this is surjective map in the zero level. But what it means, something in the zero level here, it means exactly these two maps. Like two maps, map from here and map from here, such that if I apply this, I'm going to here is the same. So these two maps actually coming from someone here, which is this exactly the lifting. Okay, so actually we have this is stronger than the lifting, but this in the zero level. So what about the one level? Actually, this tell me, the one level tell me that, because actually this means that this if we have this, then it's not just in the zero level or in every level it's surjective, it's more, it's Kan vibration. So from the Kan vibration we can get that this one actually every lifting and other lifting, if I have, because I can have two lifting, actually homotopic from the one level. We can get this. I will explain this, but there is more, of course. Like what if we have a homotopy between this and other homotopy between other, what is the relation, other homotopy, sorry, between the, what is the relation between this in the second level? It can tell me what happened here. But let me explain this point. Why like what I say so far, that this is SM7, it's stronger than CM4, it's called, I think, the lifting property. It gives us this. But in this kind of structure, when we have model category and also we have simplicial categories that we can talk about higher order homotopy. So in this case, the lifting, every two lifting are homotopies. to each other. So how we can get this? Still there is a okay. First of all, okay. Thank you. Okay. So the other, I can't. Yeah. Okay, I can move to here. Actually, we said that in this structure we have this, right? We can tensor with every simplicial set.
No.
What happened?
He ended the meeting.
Cihan ended the meeting.
Yeah.
End the meeting.
Oh,
You can. You can go. What?
He ended.
I have to tell Cihan.
Yeah. I can't start one. I did not go.
Cihan, is he? What is? Sorry. Cihan, you ended the meeting by mistake. Okay. Well, what we have to do? Okay. He is still in his office. Yeah. There is much people.